All right, so back to the handout here. On graph number 3 on that handout, I've got two functions graphed here, which they have some similarities, but they also are a little bit different. What's the same about these two here? Well, both of them, if you go from left to right, both of them are increasing, aren't they? Both increasing, right? So, as far as their, so that means a lot of different things. Their first derivatives, both would be positive, right? So both of them, their first derivatives, the slopes of their tangents are positive. Okay, so what the first derivative can't tell us is, as far as shape goes, it can't tell me how this difference occurs. Now, what is the difference here? Well, it's what's called concavity. They have different concavities. So concavity has to do with how they're bowed. This one's called concave up, and this one's concave down. Concave up and concave down. Now, so that gives you a visual for those. It can be a little difficult detecting concavity, or how something is concave up, whether something is concave up or concave down. So let's just talk about that a little more. A good example is the parabolas. An opening up parabola is concave up. So that's another example of parabola that opens up. That's concave up. The whole thing is concave up. And this one's concave down. So so here's another point to it, okay? So we've already mentioned you can't look at increasing and decreasing, can you? And this also confirms it, because what does this graph do as far as increasing and decreasing? It does both, doesn't it? You got an increasing part and a decreasing part. You got a decreasing and you got an increasing. So in concavity, you can have both increasing and decreasing. Same thing here. This is increasing, that's decreasing. So it isn't tied into that first derivative, because it's increasing and decreasing doesn't is not the same thing here. Concavity is different. Now, one thing you can use for the slope of use the tangent lines for, not the slope, but you can use the tangent lines here for concavity this way. If you'll notice, if I draw tangent lines here on this one, okay, and then I draw tangent lines on this one. One way you can tell is here the graph is above the tangent lines, right? Here, it's the other way around, isn't it? The graph is below the tangent lines. So that kind of gives you another way if you're kind of on the fence about, is that concave up or down, because they won't always be quite obvious. I mean, that's obvious. I mean, if that opens up, we usually say it's concave up, so that makes sense. But they won't all, like up here. Same thing goes here. The tangent lines are down here, so the graph is above the tangents. Here the graph is below the tangents, so it's the same, very same idea. So that can help you as well. All right, so let's go to graph 4 then and talk about concave up or down as far as the graph goes. Get this, make sure I get this right. Okay. All right, so here is up. Something like that. We'll go with it. All right. So this here is at 2. Down here is at 4. Little corner there is at 6. Seven, 8 is a little. Okay. All right. Well, so on this graph, let's try to figure out where it's concave up, and I'll just use CU and CD. Concave up, concave down. Where's this graph concave up? Where's this graph concave down? Again, we're going to use the X intervals, domain intervals. All right. Well, hopefully you see there, these aren't going to break up like the increasing and decreasing do. The increasing and decreasing break up at the peaks and the valleys. That's not the case on the concavity, concave up and down. For example, what do I have to start off with here? Well, it looks more like our little parabola down, doesn't it? Yeah, this is starting off here. This is concave down. Then in the middle here, or the next part, you got kind of a opening up thing there. So that's you got concave up there, and then you got well, all right. Let's just talk about those two. Now, does it break up at the peak? No, because like I said, this concave down is going to extend on over there. Because again, think about your tangent lines, and that's where they can maybe help you. If you think about the tangent lines, at some point those tangent lines do switch around and go from here to here. See what I'm saying? That's going to be where that happens. Is that's going to be your break in your concavity. So it's still concave down here until we reach. Let's just go with the middle here at 3. In between there, that's going to be kind of where the concavity breaks, about 3. So it goes from concave down, so let's say that's negative infinity to 3. And then it's concave up after 3 until a little ways. Figure that out. Is that okay? Is that kind of get the... So, like I said, the concavity is not going to break up at the local maxes and mins, typically. Now, we'll see something here in a second. All right. So it's concave up here, and it goes all the way to that corner. Corners, what's the derivative doing at corners? Not exist. Yeah. So we're going to have some not existing stuff at that corner. So it's going to have to break up at the corner. There's usually not any way around that. So you've got a corner, that's usually going to break up concavity too. The peaks and the valleys don't, but the corners typically do. So it's concave up until we get to that corner, which was at 6. But what is it after 6? What concavity do I have after 6? Oh, look at those tangent lines. Where's the tangent lines? They're below, aren't they? The graphs above the tangents, that's still concave up. So it has to break up at 6 because of the corner, but it's still concave up after 6. That's a little weird. Different. Is it concave up the rest of the way? Nope. Got some concave down over here, don't it? Turns back to concave down. And it's kind of where this little wiggle happens. It's concave up until you get to that point, because after that point, the tangent lines are on the other side, which means it's concave down. So I'm going to say about 7.5. That's where it's concave down here. Turns into concave down. So 6 to 7.5 is concave up, and then 7.5. Let's go with infinity. Concave down. So it's a little different than a concavity is. So just have to work a couple of those, work through those. But. All right, now here's another term let me give you before we move on to how we get it out of the derivative, this concavity stuff. The point, if you have a point where it changes concavity, that's called an inflection point. So inflection point it's a point where you have a change in concavity. And it is a point. And so it's an x comma y. Is how we generally write those, inflection point. So do I have any inflection points here on graph number 4? Yes, I do. Then I call this f of x, we've got to later. H of x. Okay? So I have a couple of inflection points here because I have where it changes concavity. It changed concavity right here at 3, didn't it? So that's an inflection point. That point right there would be an inflection point. So that x comma y, so if I'm writing out the inflection points here, one of them happens at 3, comma, the y value, which is kind of hard here because I didn't label the y-axis. So let's just, and this is typically how I do it on the others too. Let's just call it, the y value would be h of 3, right? That would be the y value with 3. And there's another one. Where's another one? Where else did it change concavity? It didn't change concavity up here at 6, but it did change it at that 7.5, I called it, by my calculations there. We had another change in concavity at 7.5, so that would be the other inflection point. 7.5 and h. So h of 7. So that's another definition or another term there. That okay. All right. So let's do this. So we've already established that it is not the first derivative that's telling me about this concavity, because the first derivative, if I was going on first derivative critical numbers, well, the first derivative critical number is at 2 and 4. Now 6 is 1, so that one's kind of a different deal because does not exist. But 7.5 would be another one. But these two here, the first derivative is 0. Those critical numbers there show me that you can't go off of the first derivative because they tell me about increasing and decreasing and local maxes and mins, but they don't tell me about concavity. You can't use those for my concavity. So what do we use? Well, it turns out for concavity, it's a second derivative. It is the second derivative. So we're going to use the second derivative to determine concavity. Okay, so here's how this works. All right, so f of x, so f of x equals x cubed plus x. Let's find where well, this is how it'll state it. Find the intervals of the concavity and inflection points. All right, so intervals of concavity and inflection point. Like I said, it's going to be the second derivative. We're going to use the second derivative here, and so let's start by finding the second derivative. The first derivative is 3x squared plus 1, and then the second derivative is 6x. So I'm going to do the very same thing that I would have done with the first derivative. I'm going to get the critical numbers, if you will, but I'm going to use the second derivative instead, okay? So, I'm going to do f prime of x equals 0 or does not exist. F double prime does not exist for these concavity, intervals of concavity. Well, and 6x equals 0, that's x equals 0. And f prime does not exist. There's not any for that. So second derivative equals 0 at 0. That's my critical number that I'm going to use. Now, what that does is that gives me these, we had those endpoints for our concavity on the previous example. These are going to be the endpoints also for my concavity, okay? That's what these give me. Should say that. We're just going to break up at concave up, concave down, just like the critical numbers of this give me the endpoints of increasing and decreasing. That's what the critical numbers of the second derivative gives me the endpoints for the concavity. So again, just kind of think about the chart here. In this case, it's at 0, so 0 breaks it up. I've got two sides of 0. Look at either side, the second derivative. All right, so here's how it works on the second derivative. If f double prime is greater than 0, then f is concave up. So it works. It works much like you would hope. If the second derivative is greater than 0, it's concave up. If f double prime of x is less than 0, then it's concave down. So when I go back to my example here, yeah, I've got 0, so that's going to break up the concavity. If I look at f prime of -1, f double prime of -1, so I'm looking at plugging that into the second derivative, so it's 6 times -1, -6. The negative second derivative, that's concave down. So like I said, that's probably like you would hope to. Yeah, second derivative negative is concave down. All right, so on the other side, again, may not alternate, concave down to concave up. We saw one example where it did not alternate, so better check it. So this side we could do a positive one, and sure enough, it is a positive, so positive second derivative, that's concave up. So we've got concave down to the left of 0, concave up to the right of 0. So we put that as an interval, negative infinity to 0 is concave down, and then concave up is 0. Good. Which also means we have a change in concavity, which means we also have an inflection point, right? Because if it changes concavity at 0, then that point at 0 is an inflection point. So yeah, we do have an inflection point at 0. And if you want to, you can just write it 0, f of 0 as the point. In this case, that's an easy one to compute. F of 0 would just be 0. So we could go ahead and add an adjustment there, but in that case it's 0, 0. Okay? And this one would be an easy one to check. If you look at the graph, x cubed plus x, oh, okay, yeah, so that one's this. And if you look at it, yeah, the tangent line's here, running there, and then they change over and the tangent lines are below. So the graph is below here, so yeah, that's concave down. The graph is above here, so that's concave up. Yeah, so easy one to check. All right. Okay, so let me just go through one more here, time remaining. Go through all parts here. Okay, so we got f of x equals x to the fourth minus x cubed plus 6. All right, so I want to find increasing and decreasing intervals, local maxes and mins, intervals of concavity, and inflection points. Because that's what I have you do on some of the homework. So it's all four, if you will, all four pieces. Well, so increasing and decreasing and local maxes and mins, that's a 2-for-1 deal. You do one, you get both. Do the work for one, you got the work for both. All right. And so both of these are off the first derivative. So f prime here is 4x cubed minus 3x squared. And so critical numbers there, that equals 0. Which would be x squared times 4x minus 3. So that would be x squared equals 0, 4x minus 3 equals 0. That's x is 3/4. Okay, so yeah, 0 and 3/4. Let me exaggerate it here a little bit. 3/4 is closer to 0 usually than that, but yeah, so I'm going to use the signs on each of those pieces. So just pull out an x out of each one of these. In this one, be f prime of -1. What would that be? It would be 4. -1 cubed is -1. So it would be 4 times -1 minus 3. -1 squared is +1. So you got -4 minus 3, that's a -7. So you got f prime negative in this, which means down. Right? All right, here I could go 0 to 3/4, so I might need to pull out like a 0.5, f prime of 0.5. Let's see what I get there. 4 times 0.5 cubed minus 3 times 0.5 squared. That's what I did. So I plug in. It's negative 0.25. So it's also negative, f prime negative. So it's also down. So we didn't have a change in change in the increasing or decreasing. And then out here we could go with f prime of 1, which is a little easier. 4 minus 3. Okay, so that's positive. F prime's positive out there. So that's increasing. All right, so yeah, I've got my increasing and decreasing right there. It's decreasing negative infinity to 0. Now, I didn't change increasing or decreasing there, but I still have to divide it up at 0 because it's not decreasing at 0. At 0, the derivative equals 0, and so to be decreasing, the derivative needs to be negative. If the derivative is 0, it's not decreasing. So at 0, it's not increasing and it's not decreasing. It's either one. So that's what I'm saying. You have to break it up at 0 still. You don't want to include 0 here. With me? I broke it up at 0. I didn't want to include 0 because at 0, it's not decreasing. Its derivative is 0. All right. Then it's increasing from the 3/4 on. Yeah, but that also gives me my local maxes and mins. To be a local max, it needs to go from negative to positive, a positive to a negative change. To be a local min, it needs to be a negative to a positive. So what have I got here? Negative to negative, so there's no local min or max there. Here I've got negative to positive, so what have I got there? So local min, right? So I've got a local min, and it's technically the function value, so it's the local min is at f of 3/4. And you can calculate f of 3/4 if you want to. Okay? All right. So that's takes care of these two. For concavity, we need a second derivative, so come here and do the second derivative. Second derivative of x would be 12x squared minus 6x. So we get the critical numbers for that, which would be that equals 0. So that's going to factor 6x, pulls out 2x minus 1. So that's 6x equals 0, 2x minus 1 equals 0, so that's x equals 0, and x equals, that'd be a half. So we're just going to do another little sign chart here on that. X is 0. Again, we'll exaggerate a little bit for a half. X is a half. Plug in numbers to the second derivative. And those pieces there, f prime of -1, let's see what we got. That'd be 12 minus 6 times -1, so that'd be 12 plus 6, 18. So f double prime is positive. Well, that tells me, f double prime tells me about concavity. F double prime positive means it's concave up. Concave up. So move on to the next one. Between 0 and a half, let's go with the fourth, 0.25. So let's do f double prime of 0.25 right there. So I'll do 12 times 0.25 squared minus 6 times 0.25. Negative 0.75. So that's F double prime negative. Well, that tells me it's concave down. And then last but not least, out here, if you do F double prime 1, that's easy, 12 minus 6. So that's 6. So again, that's a concave up, isn't it? So we got concave up from negative infinity to 0, and from a half to infinity. And we've got concave down in between, so 0 to a half. Goes off the endpoints now. Critical numbers. And then last but not least, the inflection points. Do I have any inflection points? Sure do. Inflection points are just where it changes concavity. It changes concavity at both of these, doesn't it? At 0 and a half. So 0, F of 0 would be an inflection point, and a half, F of a half. Also, it's an inflection point. Then you can figure out 0 would be easy, it would be 0.6. Half would be a little, you just have to plug that in. But if you just use F of 0, F of a half, that's fine too. All right, okay?